Hey guys, this is Lainey here to walk you through example 9.1a found in the PCI Bridge Design Manual. To provide a little bit of background information on this design problem, we are designing an interior beam for a bridge. The beam is one of 6 beams spaced at 9 feet center to center. It is a single span beam spanning a total of 120 feet. The beam will be designed as a composite beam due to the 8-inch slab deck sitting on top of the beams. A 1/2 inch thick wearing surface is included in the slab deck, therefore only allowing 7.5 inches of structural thickness when designing the composite beam. The 8-inch deck will be cast in place after all of the beams have been erected. The design strength for the concrete deck will be 4,000 psi. The bulb T will be designed to have a compressive strength of 6,500 psi, but will only be required to have a compressive strength of 5,800 psi when being transferred. The weight of the concrete is going to be the typical 150 pounds per cubic foot. Although the span of the beam is 120 feet, the beam still needs to have ample bearing. The minimum bearing length is 6 inches, therefore making the total beam length 121 feet. The pre-stressed strands will consist of 1/2 inch diameter strands made with 7 wires and are low relaxation. With this specification of strand, the area of one strand will be 0.153 inches squared. Table 5.4.4.1-1 shows the properties of the pre-stressing strand, which will give us a tensile strength of 270 ksi and a yield strength of 90% of the tensile strength, resulting in a yield strength of 243 ksi. Table 5.9.2.2-1 provides the stress limits for pre-stressing steel. Since we are using low relaxation strands, the stress limit prior to transfer is 75% of the tensile strength, which results in a stress limit of 202.5 ksi. After all losses, the service limit state is 80% of the yield strength, which results in a stress limit of 194.4 ksi. And the modulus of elasticity for the strands are 28,500 ksi. The yield strength of reinforcing steel is typical to be 60 ksi, and the modulus of elasticity can be found in the AASHTO LRFD Bridge Design Guide, which will be 29,000 ksi. Some other things to consider when designing this beam is that there will be another wearing surface of 2 inches added in the future, and the weight of the barriers will also need to be included. To keep things concise, let's skip over the detailed values for now. Before diving into the beam design, it is essential to determine the moment of inertia, section modulus, and modulus of elasticity for the beam in both its non-composite, non-transformed state and its composite state. Before we can determine the section properties for the composite beam, we need to determine the effective flange width, transformed flange width, and transformed flange area. The effective flange width is determined by the tributary area of the deck that the particular beam is supporting. Since we are designing an interior beam, the tributary area will be 4.5 feet on either side of the beam, totaling 8 feet or 108 inches. In order to determine the transformed flange width, you multiply the effective flange width by the modular ratio, which is the modulus of elasticity of the slab divided by the modulus of elasticity of the beam. This results in a transformed flange width of 84.73 inches. The same process applies to determine the transformed width of the haunch. Now that we determine this, we can find the moment of inertia for the composite area, which includes the beam, haunch, and deck. Dead loads and live loads are crucial in determining the shear forces and bending moments the beam design will need to withstand. To determine all the dead loads of the beam, we need to consider the weight of each component of the structure. The weight of the beam, deck, and haunch will all bear directly on the beam, whereas the barrier and wearing surface are spread throughout the entire structure. Since the barrier and wearing surface are considered uniformly distributed between each beam, we can reduce the dead load for the beam design. Using the typical equations for shear and bending moment, you can determine where the beam experiences max shear and max bending moment. Utilizing shear and moment diagrams will also allow you to determine the critical section for shear. Dead loads can be pretty straightforward considering that those loads are permanent and do not move throughout the life of the bridge. Live loads, however, can be distributed differently throughout the entire structure. The design live load is the HL93, which consists of a combination of the design truck or design tandem with dynamic allowance and the design lane load without dynamic allowance. In order to determine the shear forces and bending moments, we need to first determine the live load distribution factors and dynamic allowance. Once these values are determined, we can use the following equations to determine the maximum shear and moment reactions for the truck load, lane load, and the fatigue limit state. Note that all of the previous dead and live load calculations were unfactored. Now that we have determined all the dead and live load reactions, we can use load combinations and factored loads to determine the worst case scenario for the beam design. The design load combinations include strength 1 through 5, extreme event 1 and 2, service 1 through 4, and fatigue 1 and 2. Each of these combinations account for different loads acting simultaneously, so it is critical to determine which load combinations are applicable to the design. Service 1 is the load combination relating to the normal operational use of the bridge with a 70 mph wind and all loads taken at their normal values. Service 3 is the load combination for longitudinal analysis relating to tension in pre-stressed concrete superstructures, with the objective of crack control and to principal tension in the webs of segmental concrete girders. Strength 1 is the basic load combination relating to the normal vehicular use of the bridge without wind. Fatigue 1 is the fatigue and fracture load combination related to infinite load-induced fatigue life. Once the loads are calculated, we can determine an estimated number of required strands for the midspan of the beam. The Service 3 load combination is used in order to determine the bottom tensile stress at the midspan of the beam. The tensile stress is then used to determine the required pre-stress force. To determine the number of strands required, you take the required pre-stress force and divide it by the pre-stress force per strand after all losses. Now that we have an estimate of the number of strands, we can determine the composite transform section properties, which will allow for a more accurate design of the beam. Steel areas are multiplied by n-1 in order to account for the difference in stiffness between the steel and the concrete. This transformation helps in analyzing the composite section as if it were entirely made of concrete, making it easier to calculate stresses and strains under load. In order to determine the total loss in pre-stressing steel, you need to combine the sum of all losses or gains due to elastic shortening or extension at the time of the application of pre-stress and/or external loads with the long-term losses due to shrinkage and creep of concrete and relaxation of steel transfer. The time-dependent losses between transfer and deck placement differ from those between deck placement and final time. It is essential to determine the shrinkage of concrete, creep of concrete, and relaxation of pre-stressing strands for both phases. Adding all of the time-dependent losses with the loss due to elastic shortening will give you the total pre-stress losses. You can see that most losses occur prior to deck placement and all other losses are more gradual after deck placement. With deck placement, you also gain elasticity, which can be added to the effective stress in the strands. Once all the losses are determined, you can then determine the concrete stress limits and actual stresses. The difference between the stress limits and the actual stresses at the top and bottom of the beam at transfer are used to determine the finalized strand pattern. Calculating the stress at the top of the beam, you can see that the actual stress is larger than the tensile stress limit. Calculating the stress at the bottom of the beam, you can see that the actual stress is larger than the compressive stress limit. In order to decrease the compressive stress in the bottom and the tensile stress in the top, the strands need to be harped. Determining the specific harp pattern may take some trial and error to ensure the actual stresses do not exceed the allowable stresses. Since this is an example problem, they suggested we start by harping 12 strands at 0.4 times the length. Once you come up with the harping pattern, you then have to recalculate the actual compressive and tensile stresses on the beam. If the new compressive and tensile stresses are below the allowable, then you can continue with the design checks. If it is still above the allowable, then you will need to readjust your harp pattern. Now that we determined the beam can withstand all the stresses applied during transfer, we have to check all the service loads as well. The process for checking the service loads are similar to that of transfer loads. First, you need to determine the allowable compression and tension loads for the beam. Then you need to determine if the actual stresses at both the top and bottom of the beam are less than the limit state. The compressive stress due to fatigue also needs to be checked to ensure it is less than 40% of the concrete compressive strength after losses. After the beams are erected, the deck will be placed and will be part of the composite beam. So it is important to check the stresses on the beam that include any additional restraining force due to deck shrinkage. Earlier, we determined the unfactored bending moments that we can now use to determine the ultimate bending moment of the beam. Here it is essential to determine the distance from the extreme compression fiber to the neutral axis. If this value is less than or equal to the structural thickness of the deck, then you can assume a rectangular section property. This assumption allows you to simplify the nominal flexural resistance equation. The computed factored flexural resistance must be greater than the ultimate bending moment in order for the beam to be structurally sound. Now that we know our beam can withstand all the transfer and service loads, we need to check the reinforcing to ensure it adheres to the maximum and minimum rebar requirements per the code. If a beam is over-reinforced, it causes the ductility of the beam to decrease, which in turn will reduce the allowable deformation of the beam. If the beam is tension controlled, then we can assume that the beam is not over-reinforced. At any section of the beam, the amount of pre-stressed and non-pre-stressed tensile reinforcement must be adequate to develop a factored flexural resistance equal to the lesser of the equations provided. Since we know the maximum moment is at the midspan of the beam, we use that to determine if the minimum reinforcement requirement is met. The shear design is used to determine the area and spacing for the shear reinforcement. Since the minimum shear occurs at the midspan of the beam and slowly increases to its maximum at each end of the beam, we don't need the same shear reinforcing throughout the entire beam. Using the critical section for the shear, calculated earlier, we can determine the required bar size and spacing needed for the stirrups. The shear design can be broken up into a few sections to determine the different stirrup spacings required for the different shear reactions along the length of the beam. In order to consider the beam to be composite with the deck, you want them to act together to resist shear. The shear resistance will be calculated to determine the minimum and maximum rebar required. It is also critical that the interface shear rebar has the proper development length for the bar size, allowing the shear to properly transfer. Without the proper development length, the rebar could experience pull-out failure. Since the maximum shear force is at the bearing of the beam, it is important to ensure there is enough reinforcement here to withstand these forces. It is assumed that shear failure will occur at the edge of the bearing surface and the crack plane will cross the centroid of the 36 straight strands. Using these assumptions, you can then determine the available pre-stressing force and compare it to the factored shear force. The anchorage zone is located at the end of the beams and is used to confine the pre-stressed strands to avoid any potential spalling or pullout of these strands. When using pre-stressed strands, after the strands are released, the beam will be cambered. It is important to calculate the total deflection of the beam due to dead and live loads to ensure it does not exceed the maximum allowed deflection. Thank you for following along my design example, and happy bridge designing!